alpha divided by 1 minus alpha times x2 divided by x1. That's all the consequence of dividing this by this and just rearranging stuff so it's pretty. And then that's going to be equal to lambda p1 divided by lambda p2. That's the right-hand side of this thing. But then, of course, the lambdas just cancel out. And so I'm left with this expression being equal to p1 over p2, a ratio of prices. Okay, so now I've got this nice expression. I'm going to erase this middle term. Pardon? Yep. You can prove that works by rearranging them to set them both equal to 0 and then starting to cancel stuff. But this is direct. And then my next question is, okay, we have some economics jargon for the stuff in the box here too. Since this is a marginal utility, and we're dividing that marginal utility by another marginal utility, it better be a marginal rate of substitution. That's what we came up with 2 lectures ago, I think. So this thing is the marginal rate of substitution between good x1 and x2, and it's just equal to a ratio of prices. And so sort of I'll write it out, this observation that marginal rates of substitution at the optimum are equal to ratios of prices is one of the 2 or 3 fundamental things that you need to know about consumer price theory. So as a solution for market goods, private market goods, the consumer is always going to choose the consumption bundle, so their marginal rate of substitution is equal to the ratio of prices. And we take an opportunity to remind you about how this works. Graphically, if we have this commodity space x1 and x2, we have some kind of budget set. It has a slope, which in this case is p2 over p1. And the consumer is going to solve this problem graphically by finding an indifference curve, which is just tangent to the slope of this budget line. So they're going to find exactly this point where the slope of the indifference curve, which is equal to the marginal rate of substitution, is equal to the slope of the budget line. The slope of the budget line is just its ratio of prices. Is it clear? Okay, so with that, those are sort of the missing lines. Oh, did I finish solving this? No, I haven't. Sorry. Can I stop? Okay, so we're almost there. We've got this equation, which equates the marginal rate of substitution to the ratio of prices. Let me say something else about this. This is not the only point in the commodity space that satisfies this equality, because y doesn't appear in here. So if the consumer had a different level of y, say down here, his budget set would look like this. It would have the same slope because prices haven't changed, but it would have a smaller level of he'd be on a lower indifference curve. So he'd be on an indifference curve, I don't know, maybe here. And you can imagine drawing in some more. If I drew in one to be tangent to this curve, there'd be a point up here. Maybe the indifference curve is something like this. I don't know. When it gets quite wealthy like the Beatles, you can go up here, or something like this. Okay, so you can imagine filling in lots of these different budget lines for different values of y. That would trace out, we'll come back to this. That would trace out a set of points where the slopes of the slopes were all equal. This line, by the way, is called an isocline. We'll come back to that later. So the point is that this equation tells us that the solution to the consumer's problem lies someplace on this isocline, but by itself it doesn't tell us which point. Okay, so what's the other piece of information we need to figure out the point that's going to pin down consumer demand here? We need the budget constraint, this neglected but critical equation over here, and that tells us what y is. And so that tells us which one of these budget lines is the one that's relevant. So graphically, maybe y corresponds to this budget line, and so that would allow us to pick out this point as being the optimum. In terms of doing the algebra, what we can do is take this equation, which involves 2 unknowns, x1 and x2, this equation, which involves 2 unknowns, x1 and x2, and then there's a couple of different ways you can do it. The way I would proceed here is probably to rearrange this thing. So we have x2 expressed as a function of p1, x1, p2, and y. So that would give us, let's see if I can do this, x2 would be equal to p1 over p2, x1, minus that, and plus y divided by p2. So here's an expression for x2 in terms of x1, y, and the prices. Then I can substitute this expression for x2 into this equation. That gives me, so let's call this bc, and let's call this star. So if I combine bc and star, so bc is the budget constraint, star is this marginal rate of substitution being equal to the ratio of prices, we'll have the result, we'll have alpha over 1 minus alpha, all times p1 over p2, x1 plus y over p2, all divided by x1. That'll be equal to p1 over p2. And now I've got an equation which depends only on a single unknown, that's x1. I can solve this thing for x1, and hopefully it turns into that thing up there, that top line. Yes? Oh, there it is. I forget my minus. Thank you. Yeah. Okay, so I solved this thing for x1. That gives me the Marshall demand for x1. I'm going to omit those intermediate steps because I'm likely to make mistakes since I'm standing in front of you here. And so I think I'll wind up with x1 equal to alpha times y over p1. Actually, I know I will, which is the expression I have up here. I can then plug in, take that expression for x1, plug it back into the budget constraint, and that'll kick out an expression for x2, which will be x2 equal to 1 minus alpha y over p2. Okay. And that's the stuff here. Okay, so this is the Marshallian demands. And again, we'll use this particular utility function often because it's not crazy and it's very convenient. But Marshallian demands in general are going to tell you what demand is going to be as a function of prices and of income. And they'll be defined for any sort of well-behaved utility function. All right, questions? All right, let's forge ahead. So I want to give you one generalization of this thing. So we've been working with this thing. We just talked about a function that involved alpha times the log of x1 plus 1 minus alpha times the log of x2. We use that as our utility function. It's handy to be able to generalize that, and it's really easy. So I'm going to do it quickly. I'm going to tell you what the generalization is rather than solving it for you. So an immediate generalization of this thing to n goods instead of just 2 involves writing the utility function this way. So we write the utility if you have n different goods you care about, so any finite number. We can write this thing as the sum of a bunch of logs of the goods we're consuming, weighted times these reference parameters alpha. So what we just did a moment ago was a special case where the weight for good 1 was alpha and the weight for good 2 was 1 minus alpha. This generalizes. You can have alpha 1, alpha 2, alpha 3, and so on. It's convenient but not important to assume that the alphas all add up to 1. And this is an example of what's sometimes called a Cobb-Douglas utility function. There's a couple other ways to write it. This is how I'll generally do it. So we can solve the consumer's problem for this thing involving any finite number of goods with not much more difficulty than we just had in solving it for 2, actually, but I'm not going to do it in class. Let me tell you a little bit about some of the consequences of that. We get some Marshallian demand functions. Actually, do I tell you what they are? No. Okay, I better write that down. we get a Marshallian demand function for these preferences, which just looks like this. We have demand for xi as a function of prices and of income that'll be equal to alpha I times y divided by pi. So I, of course, can take the value, any value 1 to n, since we have n-goods and consumers choosing everything. So with these more general preferences, this is the form that Marshallian demand takes. And I hope you can see just immediately that the two-good case we've done is a simple special case of the in-good case, for which this is the solution. All right, questions? Okay, let's, I'm not sure. Are there really no questions? You guys are? Yes, this comes from an assertion. But the way you'd solve it is you'd start, so suppose this is the utility function you had instead of this. So can you see that this is a special case of the other one? Where you just take alpha 1 would be this alpha and alpha 2 would be 1 minus alpha. So this is the special case of that one. We can write the Lagrangian here, and we've gone through how to solve that. But we can also do it for this case, this general case, where we get a first order condition for every one of the n-goods plus a budget constraint. So our Lagrangian in that case actually isn't that much more complicated. The Lagrangian in the n-good case would look like this. It would look like the sum. Is everyone familiar with summation notation? This just means we're going to add up all the objects that live next to this. So we're going to sum I equal 1 to n of alpha I times the log of xi, plus we still only have one budget constraint. So we'll have lambda times y minus the sum I equal 1 to n pi xi. That's our budget constraint. And then first order conditions for this are a lot. I mean, they're essentially identical to the ones we had before. The first order condition with respect to a generic good xi will just be alpha I divided by xi minus lambda times pi. So that's the partial derivative of the Lagrangian with respect to good xi. And then finally, of course, with respect to lambda, we get the same thing we had before, namely y minus p minus the sum of these things. Your expenditure is I equal 1 to n pi xi. Okay, so it takes really exactly the same form we had before. And you've got n plus 1 equations instead of 3 equations. But since these all take the form, it's not difficult to solve. Yeah, Hillary.
I know right now we're assuming that because they're non-substitutes, will we get the where the UIs completely kind of price on.
So Hillary reports correctly that we're assuming that there's no substitution, that these goods aren't substitutes for each other. I actually wouldn't say that's what we're assuming. That's a consequence of the utility function we've got. So this utility function does in fact imply that there's no substitution between goods. These methods apply to much more general utility functions that do allow for substitution and complementarity. This one makes it easier. Like what he said. We will a little bit. The algebra gets harder really fast, and so I'm trying to give you simple examples right now. But yeah, we'll certainly consider this. Yeah. Okay. Other questions? I don't want you to fret up. Yes. So when we solve this thing, so we get a solution which I've written, which I still haven't written. Did I write it? Yeah, it's here. This is the Marshallian demand. This is the solution to the problem. So it says the Marshallian demand for good I is equal to the weight alpha I times income divided by pi. So this remark about, do I say this? Yeah, depends only on own price. It's just an observation that for the ith good, only the ith price matters. Your total income matters, the ith price matters, no other prices matter. And that's the observation that led Hillary, I think, to observe that there's no substitution going on here. If there were, these demand functions would have the prices of other goods in here as well. Okay. All right, so yeah, good question. I don't want you to worry about this too much. This is meant as a shortcut so that you can easily extend the work we're doing for two goods, or think about being able to extend the work we're doing for two goods to an arbitrary finite number of goods. We're not really limiting ourselves with the two-good analysis as much as it may seem. All right. Okay, so I'll make some observations about this. This is true for n-goods. It's also true for two goods, of course. So the parameters alpha I, when they sum up to 0, I think I already said this last time, they're equal to the expenditure shares. So you can see that immediately from this equation. If I multiply both sides by prices here, I get price times quantity of x1, so that's expenditures, xi. That gives me expenditures on good xi, and it'll be equal to alpha I times y. So that tells us that alpha I is equal to the share of your total expenditures devoted to purchasing good xi. So alpha I is an expenditure share. It has that interpretation for these preferences. The Engel curves, this is also reviewed from last time. The Engel curves are linear. You can see because this expression is a linear function of y. The Engel curve for this thing, or this is the Engel curve, is xi expressed as a function of income. Passes through the origin because if y is equal to 0, demand is equal to 0. And it'll have a slope equal to what? So I'm just graphing this thing as a function of y. So the slope is equal to alpha I divided by pi. Is that not apparent? So for every time if you start with y equal to 0 and you increase it to 1, then xi will be equal to alpha I divided by pi. So it just depends on the slope. So linear Engel curves, slope is given by this expenditure share divided by the price. So if prices increase, the slope of the Engel curve falls. All right, what else? We talked about this last time also. If we graph this thing as a function of its own price, so if we have, we have quantities and prices. I'm going to do this upside down like Marshall. We get something hyperbolic because xi is equal to yi divided by pi. So we got a hyperbolic sort of demand curve when we vary on price. And we already made this observation that demands only depend on own price, not the price of other goods. Okay, so these are statements which are true of the two-good case, which we've now sort of gone through twice pretty carefully. It also extends just immediately to the n-good case, which is nice. All right, questions? Let's go. All right, so I want to talk now about monotonic transformations of utility. So this is a topic we've spent some time on before. I want to give a sort of direct demonstration today about how monotonic transformations, how those things may affect demand. Okay, so I'm going to define a function f here, or a transformation f. And so f is a function in this case that maps the real numbers into the real numbers. And it's increasing. It's strictly increasing. That's going to be necessary for it to be a monotonic transformation. So if we have any x prime which is bigger than x, it follows that f of x prime is bigger than f of x. That's what we mean by a monotonic function, or for a function to be strictly increasing. Okay, the assumption clear? Great. All right, so now let's say that we have a consumer who has a utility function like what we had before, maybe that sum of logs. That's the utility function. And we have another consumer who has that utility function, but instead of that, we're going to take a transformation of it. So the utility for the second person is f of u of x1 and x2. Okay, so that's called a monotonic transformation of u. And so the question we have here is how will demands depend on f? As you guys may already have some views, some reasonably well-informed views on that subject. Any reactions? How will demands depend on that transformation? Yes. Okay, so tell me your name again. I'm sorry. Taichi. Taichi says maybe it won't depend on f at all. That sounds reasonable. Who agrees with Taichi? Who disagrees? Who's afraid to raise their hand for fear of being called on? Okay, so yes, in fact, it will turn out the demand doesn't depend on this transformation f at all. Let me show you why. Okay, so actually, let me say something first, because you already kind of know why, because you know, having dealt with it in the last problem set, that marginal rates of substitution won't depend on there being a monotonic transformation or not. But so let's go through it here for this exercise, though. So let's think about the consumer with the transformed utility function. So she's going to want to think about maximizing f of u of x1, x2, because that's her utility function, and she's going to have to satisfy the usual budget constraint here. Okay, so that's her problem. Okay, so is that clear? So instead of maximizing u, we're maximizing f of u. Now the question is, how does demand depend on f? And here's the answer. At the optimum, we'll have the budget constraint that still has to be satisfied, and we'll have some first order conditions, which are very similar to the ones we've gotten previously. We'll have what we had before. I don't know how to reach up and shade this here, but ignore this f prime piece. This piece here, du dx1 equal to lambda p1, and du x2 equal to lambda p2. Those are just the conditions setting marginal utility equal to something proportional to the price that we saw a little bit ago for the case where we had u equal to alpha log x1 plus 1 minus alpha log x2. Okay, so if I were to draw a line here, the stuff on the right should look very familiar. Okay, there's a new thing here, though. We just get this in the chain rule. There's another term, f prime of u, that enters into these first order conditions. So this is new, and it's showing up because of the transformation we've made to the consumer's utility. All right, so is that all okay? This is quite precisely analogous to what we did when we worked with Lagrangian previously. But I still see some puzzled looks. Anyone care to express puzzlement in a specific way so I can address it? Okay, so is it clear where these things are coming from? The problem I would write down here is Lagrangian, where I would maximize just the Lagrangian for this. So I define Lagrangian, which is f of this plus lambda times 1 minus p1 x1 minus p2 x2. It's the same problem I wrote up on the board a little earlier. Okay, so I write down the Lagrangian. I take first order conditions. The first order conditions take the same form they did before, except because I've got this transformation f, I get an extra factor here on the left-hand side, f prime of u, here and here. All right, so that's clear? I'm going to go ahead. Okay, so now we've got these first order conditions, we've got the budget constraint, that's all familiar. Now I'm going to do the same trick I did before, dividing one equation by the other equation. And here's the beautiful thing. I'm dividing the left-hand side of that equation of the first equation by the left-hand side of the other equation. And so this is just what I did before on the board. And it's equal to lambda p1 divided by lambda p2. But here a couple things cancel out. The lambdas cancel out on the right-hand side, just the way they did before. But also these f prime of u's cancel out. This is just f prime of some real number. And it's the same real number here and the same real number here. So the f primes cancel out. And we're left with the result that the marginal utility of u, the partial derivative of the original utility function u, not its transformation, that this ratio of marginal utilities is equal to the ratio of prices, which is exactly the condition that we would have had for the original consumer without the transformation. Okay, so to solve the Marshallian demands, we take this condition and we take we take the budget constraint. This doesn't depend on f. Neither of these things have an f in them. So when we solve for the demands x1 and x2, they don't depend on f either. So they're completely independent of the monotonic transformation. F disappears, and so we just proved that f can't affect the consumer's demands. And so we'd say more formally, the demand system is invariant to monotonic transformations of the utility function. Okay, so here's a follow-up question. Is it the case that the value function of the indirect utility function is similarly invariant? And since let me come back to that in a moment. Okay, so before I come to indirect utility functions, I want to briefly define some more mathematical jargon for you. You may have seen this stuff before in a previous math class. So I want to define for you a homogeneous function. So if we take a function g of two variables, x1 and x2, we say that that function is homogeneous of degree k if it's true that when we multiply all the arguments to the function by some positive constant, some positive scalar b, that the g of b x1 bx2 is equal to that scalar b raised to the kth power times the original function evaluated at the original arguments x1 x2. But I don't have any wonderful intuition about this except to say that you should think about this b is imagine the b is equal to 2. So what you're doing is saying something like, well, gee, suppose I double the amount, and you can think about this g as being a utility function or a production or function or something. If I double all the inputs or all the consumption, what happens to the outputs? Or what happens to utility, if you want to use that example? And not all functions satisfy this. I mean, very few of them do, in fact. But if they do, if a function satisfies this expression, or this condition, we say it's homogeneous. Okay, so this is probably a place where some examples would be helpful. So